Welcome, everyone. Thanks for coming to this talk. Today, I'm Dwight Whitlock from Clinician Nexus. I'm a data platform architect here. So today I'll be talking to you guys about how we process some of our human-curated data and the developer tools that we used in the process. So you've probably seen this slide 5 times by now. Doesn't really apply to us because we're not doing anything, top secret. My personal disclaimer is I hope you've seen Office Space. It is a comedy if you haven't seen it. So the internal name of this project is Red Stapler. It's a reference to that movie. And in that movie, everyone processes TPS reports, which if you've processed data, you can probably relate to. And that's our fictional schema that we'll be talking about today. And I have to assume some level of background knowledge when I'm giving my talk. So I assume that everyone is at least a junior data engineer. I'll try to explain all theory as I get to them, but I'll have to move on for time's sake. And this is a technical talk, but I will explicitly mention business value at the end. So let's talk about our data at Clinician Nexus. So Clinician Nexus collects compensation, performance, and job classification data from most of the major health systems in the United States. And so our analytics is around physician compensation. And for better or for worse, we have to rely on human-created files. And there's a variety of legal and technical restrictions that you can imagine if you're working with the most regulated industry in the most, fractional regulatory state of the US. So at the end of the day, we have to rely on someone essentially copying and pasting their data into a spreadsheet and sending that to us. And this is very important data to us. It's the input to a bunch of different products that we sell back to our clients. And so data quality is very, very important. So let's talk about what one of those reports that we get looks like. You might notice that this is in Microsoft Excel, which everyone loves working with. If you look at the first column, you might see that there's bad primary keys. Foobar is not an integer, and that might cause some join concerns. We have missing data types. Our enumeration's all over the place. Our date formatting's all over the place. If you've dealt with raw data, this is the kind of stuff that you get to deal with. So when you multiply this by the scale and complexity that we have to deal with, it is not a good time. So we have many different survey schemas that we send out and clients will send back to us. And for every one of those schemas, there can be up to hundreds of sub-publications. So you can imagine most of our clients aren't going to be interested in the median physician compensation overall. You might want to know the median heart surgeon annual cash compensation in the state of Georgia. So when you continue to add filters on that query, your data, the number of rows in your data set keeps lowering. And when that happens, the impact that a single row can have on your data quality keeps increasing. So with all of these different surveys, there are thousands of submissions per year. We've been at this for a very long time, so we have many, many years of history, and the healthcare market has not stayed the same in the past 30 years. So therefore, the information that we have to collect about our clients is going to change as well. So we have to expect that schema evolution is going to occur. So let's recap and talk about what the business is asking of us. Number one, we need consistent validation of data types, missing fields. This is easy bronze to silver layer stuff that most everyone has probably worked on. Next step, we need to be able to clean our rows over time. So it needs to be iterative, and our analysts need to be able to go and see the history of changes. So we call that auditable row level cleansing. Our system has to be fast, scalable, and cost efficient. While our pipelines aren't going to be running all of the time, our statistics show that people are procrastinators, And if we have a deadline for survey submissions, everyone's gonna submit on the very last day. And so we have 0 traffic for 364 days, and then a monumental amount of traffic on survey submission deadline day. So if we can't adapt to that, then I'm hosed. Next up, we need to be able to govern schema evolution in a reasonable way. So I mentioned that the healthcare industry is always changing, which means our schema is always going to be changing. And if we don't have a really tight process for that, again, bad. We have a lot of different survey schemas, and this is a very common business application at Clinician Nexus, and so we need to be able to maintain it and apply it to other teams. And also, I mentioned we have other SaaS products. That means we have multiple data consumers. So we're not just talking about analysts within the data lake. I'm talking about other applications that need real-time access to that data. And so our stack needs to support that. So before I get into the architecture, I need to cover some of the foundational theory behind it. So if you've taken a data engineering class, you've heard of unstructured and semi-structured data. Unstructured is your text, your images, your PDF, things that you can't read into a data frame. Your semi-structured is a JSON, CSV, something that has some inherent format but is not consistent. And at the other end of the spectrum, you have strongly typed systems like Delta Lake or most other database management systems. So I mentioned that before, most of our file ingestions are based off of Microsoft Excel. So you might ask yourself, well, where does that fall in? In my opinion, it's somewhere between unstructured and semi-structured because it is a very complex proprietary data format. And so if you've ever worked with trying to read Excel into a data lake, I have a word of advice is don't. Date formats are not pleasant to work with, among many other things. And for those reasons, there's no direct Delta Live Tables integration. So if you've done some loading files into a bronze or silver layer, you might have used JSON-based autoloader or CSV-based autoloader, where Databricks will infer the schema for you and manage the schema evolution. That's not the case with Excel. And my theory is that is a pain in the rear end, and so they chose not to do it. So this system is to accommodate that lack of DLT. Talking about schema evolution. This is a pretty simple concept where our business users are going to come to us and say, this column doesn't make sense. I need to change the data type from a string to an integer. Or this field's not relevant. I'm going to stop collecting it. Or I need to rename a field or add a field. All these are very common use cases that we get all the time. And so our job as data stewards and data engineers is to then ask, how severe are your changes going to be? Are your downstream data consumers, are their pipelines going to break? Is it a non-breaking change? Can this just be a deprecation, et cetera? So when thinking about schema evolution, you shouldn't think about just the semantics of an alter table, add column, or drop column. You need to think about the people process behind it. And so without a good people process behind it, you're going to have lots of business people coming to you and asking you unpleasant questions like, this metric that my entire report is based off of, it disappeared for the year 2024. Why did that happen? I own this domain and I wasn't aware that this change was introduced. Again, stuff that is not fun. And so our job as technologists is to then ask, what technologies can we introduce to the enterprise to make this more efficient and more scalable? And that leads us into, one of the foundations of this talk, which is the protocol buffers message format. And so, AKA Protobuf. Protobuf is a cross-platform schema language that is language agnostic. And so what that means is that you define your schema in .proto files, And then wherever you want to use those, like in a gRPC service or on Apache Kafka, you compile that into your runtime language, and you can use that. Protobuf is smaller and faster than JSON and XML, and it's the backbone of gRPC, which is you're probably already using if you're using Spark Connect or Kubernetes, or if you've ever seen a talk from Google, Netflix, or Spotify. So it is already ubiquitous, and this tooling's not going away. And so what I'll show today is that the developer experience around the Protobuf ecosystem can be significantly better than alternatives like a JSON-based Kafka pipeline or an Avro-based Kafka pipeline. So I talked about structured and unstructured data types beforehand. Protobuf is very strongly typed. As you can see, every field has a data type associated with it. It has an index. And without getting too far into what the index is responsible for, there's also key value pairs after the index value. And so these key value pairs are where you can store metadata for any given field. You can also do this at the message level, so you can have object level metadata. And we need to be able to write pipelines that are configuration driven. And so this is really easy to use for simple pipeline logic, like, okay, what is the header name that I need to read from this Excel file? Or if we want to add a little bit of complexity, if I'm building a parameterized SQL query, what's the primary key? And so you might then be asking, well, you can do schema-driven and parameter-driven development all within the native Spark ecosystem. So if you've done a dataframe.schema, you'll get an object back called a struct type. And that is a Spark class that defines what your fields are, what your data types are, and it has metadata associated with it. So going back earlier, I mentioned that we have many different data consumers and data producers. If you're not running Spark, you don't have access to struct type. And so this is not friendly for a Go-based microservice. So Protobuf is a whole lot better here, and it is the underlying technology behind gRPC, which conveniently is how our microservices communicate to each other. So again, we have both file-based data sources, and we have other internal applications that are both data sources and data consumers. Okay, so my next topic is a tool that really makes working with Protobuf just a whole lot better. It's called the Buf Schema Registry. They have a booth down at the expo if you want to check them out. But they are the kind of what makes working with Protobuf so much nicer than working with Afro. I talked about breaking change detection and how that can just be the nightmare, can be a nightmare in your schema maintenance. You can do automated breaking change detection with the Buf CLI, and they have a CLI tool and their schema registry, which is a UI. And we've set up GitHub Actions to essentially automate the detection of breaking changes versus a non-breaking change. So in this example, I commented out my ID column, which is a bad idea. And you'll see at the bottom that our GitHub action says, that's a bad idea, you shouldn't do that. And so you can configure whatever your schema evolution rules that you want, but Buf comes with a really robust set of defaults. In addition, with Buf, you get really nice API documentation. So if I'm developing an API, whether that's gRPC-based, or if I'm developing a schema that all of my data engineers are going to communicate with, I need to be able to communicate what that looks like and the business context behind that in a good way. With Buf, you can write Markdown within the comments of the schema and have that render into this very nice UI. You can click and see embedded schemas, and it's very, very easy to use. One one of the most important things that we've seen with working with Buf is that they have really good dependency management. So in this screen, we can see our, my data platform proto repository. And I am referencing data types that are not just based in the native proto. They're based off of the Google APIs object. And so you can see that I have a direct dependency on Google APIs, and you can see the exact version number should you need that in your debugging. And this works exactly like Poetry lock or a Terraform lock if you're familiar with those systems. And it also means that you can use Protobuf and not need a monorepo. Whether monorepos are good or bad is outside of the purpose of this talk, but it gives you more flexibility. So you can have one team or our centralized data platform team define the common configuration, and then you can have consumer teams call those dependencies in their schema repositories. So that's what you see at the bottom with the, you can see the direct dependency graphs. I mentioned that Protobuf is language agnostic and can compile into many different languages. If you've worked with tooling like that before, at least like OpenAPI or Avro, that can be very unpleasant if you're just trying to generate code based off of a CLI, especially when you get into version management and integrating with Git. It's unpleasant and makes it just another barrier of entry into doing this kind of development. The Buf Schema Registry automates all of that for you, and you have for essentially every version of your schema, whether that's via a commit hash or a branch, you can generate SDKs based off of that. And so, our team primarily uses the Python SDK generator, but they have generators for all major languages. And this also makes testing schema changes really easy. So if I'm writing a configuration-driven pipeline, chances are that if I'm adding a new feature, that means a change to the configuration, and I can then go and test that via my, this version of my schema registry before I push that change to production and make my consumers upset. So in the top right, I'm on the breaking change demo branch. Okay, last up, I mentioned Apache Kafka before. It's a distributed streaming platform, publish once, read many times. So we use this to send Protobuf messages to something, and then many different consumers can read it. It's the de facto standard for most real-time analytics applications, and they recently support Protobuf. So we combine our usage of Protobuf and Kafka so that any application that is consuming or producing data can consume it as well in our microservices architecture. So if you're talking about schema governance and streaming platforms, it's worth mentioning the current state of schema registries. So if you're familiar with Confluent, they have their own version of a schema registry that works with the Kafka cluster. That works with open source Kafka. And there's offerings for this with Amazon MSK with a Glue schema registry. If you're running Confluent, they have their own, et cetera. But essentially, this is all reactive governance. You are reacting to messages as they arrive to determine if this is a breaking schema change or whether this is a valid message that can be on the topic. What we can do if we have kind of more a proactive approach is prevent breaking changes from being introduced. So if you're working with the Buf Schema Registry, you can detect your breaking changes at pull request time and have your developers respond to changes before the action is taken. And it's worth noting that if you're using the Buf Schema Registry, they also implement the Confluent Schema Registry, so you get kind of the best of both worlds. Okay, so all of our basics down, let's talk about how we have implemented our pipeline. Coming back to our requirements. We talked about how to validate our data types with our strongly typed mapping of Excel schemas to Protobuf. We talked about how we can govern that schema and how our Protobuf-based architecture allows for many different consumers and technology stacks to interact with it. Now we need to cover how we can clean rows over time, the performance attributes of it, and how easy it is to maintain and apply to other teams. So data cleaning. I mentioned before that we process human-created data. Therefore, we have to assume that there are errors in it. And so we have a business process where we go through and clean the data in basically different tiers of complexity. And so in the very basic tier, let's say there's a metric that was just erroneously put in, and it should be, we're just changing it from X to Y. That's pretty simple. The next tier of complexity is, I've run an analysis on Bob's TCC, and it's a huge increase from last year, and in reality, we shouldn't be seeing those numbers, so can someone go take a look at it? And then we have additional complexity, which is something like, for this very specific sub-filter of this query, so for all hospitals that are of a small organization type, this guy's TCC is a statistical outlier. So all of these different things impact our data quality, and because we can have publications that are based off of basically tiny data sets, this is really important. And there's a lot of different tooling out there now that can help detect anomalies automatically. So you can do business rule-based anomaly detection or machine learning-based anomaly detection, which Delta Live Tables has recently announced features for. There's also Monte Carlo, Big Eye. But there's no industry standard on what to do once you've identified those anomalies. And so our process for once we've identified that something is erroneous, how we can give that information to our publication teams is our competitive advantage. And so, this data cleaning process can be pretty complex. So we had to build a application to support that. And internally, this is known as the data workbench. And this shows an example survey submission with about 10,000 rows. The vast majority of those rows are clean. We don't see any issues with them. There's one row that has a breaking change. There's a few rows that have a non-breaking change. And then there's 250 rows with an attribute called DNP. And what that means to us is do not publish. And this is a very complex nested data type that says we shouldn't publish this record because this attribute on this field looks weird. And so you can imagine at the scale of hundreds to thousands of different publication types, this object can get pretty complex. So because we have this UI to help clean our data, this is an example of one of the SaaS applications that have to supplement our file-based data ingestion. Okay, so I talked about how basically the new source of our changes to the data. Let's talk about how we actually represent that in Databricks. So we use a table format called slowly changing dimensions. And this is a industry standard table format, which is basically a normal table with primary keys, except you can't update and you can't delete. So it's append only. And when you attempt to make an update or a delete, it just updates the start at and end at columns to say this record was valid from this time period to this time period, and now this most recent one is the current one. And luckily, Delta Live Tables makes an API that makes this really easy to implement. So that's the DLT Apply Changes API. And so We can define a pipeline that says we can track all versions of all changes to data if it's a do not publish marker or a change in the source value. We can track all of it so that our analysts know the history of everything, basically. And so this is a diagram showing our the deployment level for this. So on the left, there's the file ingestion side of things, and then on the right, there's the Protobuf processing side of things. So when we receive a file, this will kick off a Databricks job that then triggers a DLT, and this will just read that file from S3, do some cleaning, some validation, and then eventually it will write that data in Protobuf format back to Kafka. And there's a few reasons for this, which I can talk about probably after the talk. But essentially, once we finish writing to Kafka, this will then trigger our Protobuf processing DLT, which reads Kafka, and then does a Spark read Protobuf to transform it into a tabular format, and then into the SCD Type 2 table. On the file processing side, I mentioned that there's a series of transformations that we make. So we might need to flag certain things in the file processing side for our data quality analytics. So like if someone sends in a file and there's 2 invocations of the same primary key, that's a problem, and we should probably give our analysts a warning about that. So we have duplicate detection. We have basic cleansing steps like strip out leading zeros, that kind of stuff. And then finally do our casting from our unstructured string-based Excel input to our strongly typed casted output. On the Protobuf side, it's a little bit more straightforward. You start out by reading from Kafka, write that to a sync table, and then after you have the sync table, you can do read Protobuf into your tabular format, write to the slowly changing dimensions type 2 table. And once you're there, this is a DLT. And so you can do all of the nice things that DLT has built in, like data quality, expectations and validations, anomaly detection, and for us, we do materialized views based off of what data meets our quarantine standards or is completely invalid and has to be fixed, and what data is valid. And because these are materialized views, they're really fast to update, and DLT handles all the heavy lifting behind the scenes. And so all of this is to try to minimize the time to our to data quality error resolution time, because the people giving us their data, that's not their full-time jobs. And if we keep pestering them and saying, please fix this issue and then fix this issue, they're just not gonna be, I wouldn't like that. So we need to facilitate that, improving that user experience. So that's why we chose to have this pipeline be event-driven. So as the clients submit their data, we will process it and detect data quality issues, look for anomalies, and communicate that in a fast way to our analysts that are facilitating that ingestion. We use serverless compute, and that allows us to have a very fast compute time. If you're doing any kind of batch file processing, the startup time associated with that is just doesn't work. Additionally, we maintain all history with the SCD Type 2 table. So if there is a sequence of edits that aren't necessarily correct the first time, we can go and see exactly what happened. And every transformation in this architecture is a DLT. So again, you can go and see if I have this row that looks really weird, maybe it was a casting issue at this point upstream in the pipeline. So some performance results of our testing. Generally, it takes about 2 minutes to process a file, and the vast majority of that is just the serverless cold start time. When we apply it to larger files that we receive, that goes up to 4 minutes. And this is before we get into any partition or cluster by optimization. So pretty reasonable results. And I will say that our survey processing is an annual business event or quarterly. And so millisecond latency or second latency is not our priority. We need to, it's better for us to write everything to disk in a bunch of different places so that we can debug that much faster. On the cost efficiency side of things, everything is DLT based or DLT serverless based. So we only pay for the execution time. And then on our messaging layer, we're paying for the Kafka compute time. And so if we have idle compute, that's going to be a large source of costs for us. So if we can get down to, when this pipeline's not in use, nothing's actually happening, that's our ideal cost scenario. So to facilitate that, we ended up choosing to use Bufstream, which are made by the same people that made the Buf Schema Registry. And it's a Kafka offering that has native support for Protobuf and integration with the BSR. And very conveniently, it meets our requirements of scaling down to 0 when not in use. And it does this by being based off of object storage. So I personally don't care that my Kafka message can get to a consumer within a second. I'll trade off, an extra 2 or 3 seconds of latency for the ability to not have to write to something that's always running on that disk or that memory space. And it's worth noting that they have some really cool features for analytic pipelines that we haven't started using yet. So one of the big things is Apache Iceberg integration, which is now, Iceberg is now a natively supported table format to Databricks. So essentially, you could have a Kafka topic and then persist that into your lakehouse without any additional configuration. So we'll probably be using that in the future, but worth noting. And so for onboarding new pipelines, the process is essentially just working with the business teams to define their schemas and put them in Protobuf, define the metadata associated with that, and register that in our schema registry. If they have a source of data for that, like an S3 bucket or some application, we just register that in Unity Catalog, and then we can deploy this workflow for that schema configuration and integrate it with the data workbench. So again, our goal is no ad hoc ingestion for our most important data assets, and the pipeline onboarding is driven by our business users. And so with that, I will transition to a very short demo. Let's wake up my computer first. Okay, and so what this demo shows is basically a sequence of file ingestions and the different data quality events that can occur. And then after each of those events happens, what our tables and views look like to our downstream analytic users. So at time 0, we just upload a file with an ID. At time number 1, for that file ID, we're going to introduce some issues. So let's say that I have a batch of data arrive where there's conflicting sources of information for that row. That should probably go to our quarantine step. At time 3, our analyst says, that's no good, I need to fix that. So they submit another file that says, this is actually the latest source of truth for this. And then inevitably, time goes on and someone else breaks it for a completely different reason, and you have quarantine data again. So this will just walk through that specific, what that looks like in these tables. So at time 0, we upload a file with ID 574, and this shows up in our SCD2 table, and we can see that it's the most up-to-date row because the indat column is null. So if the indat column is null, it's the most up-to-date. This is valid data because our column called QC metadata, or quality control metadata, is empty. Now we move on to time 1, and we upload a file with conflicting sources of information for this ID. And this is starting to show up in our quarantine view. And there's information in QC metadata that says, oh, crud, that's bad. We broke this specific business rule, and so I'm going to store this on the record so that someone can then see that and fix it later. Okay, so now we try to, sorry, here's the SCD2 table for that. So upload a fix and then show the SCD2 table. So we've uploaded our fix of the duplicate data, and now we have 4 different rows. We have our original row, our 2 quarantined rows, and the fixed. So first one is fine, there's no QC metadata. Number 2 and 3 are duplicates and are quarantined, and number 4 is looks good. And number 4 has a null indat, and therefore it is valid. And let's query the quarantine view again. It's empty. We didn't have to do any updates outside of just updating a new or sending in a new file. And now let's break it for something else. The QC metadata this time is going to be if I can find it. Okay, so this file failed a null check. So we expect that different data quality issues are going to appear all of the time. And so basically the process by which we can identify those and rectify those is important to our business process. Okay. So talking about just a few of the implementation challenges that we had, we work with healthcare data, and so we have to exist within a HIPAA-compliant workspace. And generally, that means that anything that's a preview feature, we don't get until many months later. So as we were working with the latest offerings of serverless compute from Databricks, we were essentially struggling to keep up with their struggling to just get all of the features that we needed. So we couldn't do things like read metadata from S3 because instance profiles are not a thing in serverless compute. You need service credentials. Or serverless compute requires a completely different dependency configuration than traditional compute. Or the serverless runtime is way stricter than general compute. So those were some challenges. And then anytime you're developing with if you're trying to do schema-driven development, you need to understand the API of that schema. And if you're working with Protobuf, that's the descriptor proto API. And I have linked in the slides, which I believe will be on the Databricks website, a link to an article from Buf that talks about all there is to know about the descriptor proto API that I wish I read before I started. Okay, and that is all. Thank you. And thank you to Tarmac and Buf. I think I saw Mary in the back from Buf. And then a ton of people from Clinician Nexus and Tarmac are here, in addition to Diego. So yeah, thank you.